इस पे जो क्वेश्चंस आते हैं दे मे नॉट बी स्ट्रेट फॉरवर्ड क्वेश्चंस, दे मे बी ट्रिकी कॉम्प्लिकेटेड क्वेश्चंस। ये क्वेश्चंस ऐसे डालते हैं बेटा कि आपको अगर उसका कॉन्सेप्ट क्लियर नहीं है तो आप उसको आंसर नहीं कर पाओगे। सो शुरू से लेके लास्ट तक हमें पहले तो इसके कॉन्सेप्ट्स को वन बाय वन समझना पड़ेगा। इसमें हमारा काफ़ी टाइम भी जाएगा, बट विदाउट स्पेंडिंग दैट टाइम हम लोग इन क्वेश्चंस में प्रोफिशिएंट नहीं हो सकते। सो हमें इन क्वेश्चंस में टाइम डिवोट करना है। फंडामेंटल्स को पहले सीखना है, फिर फंडामेंटल्स को अप्लाई करना है। इस पे स्ट्रेट फॉरवर्ड क्वेश्चंस कम आते हैं। लाइक कोई आपको सीधा कोई स्ट्रेट फॉरवर्ड क्वेश्चन दे दे कि भाई एक्सप्लेन कोफिशिएंट बी, कोफिशिएंट ब्रेवो, कोफिशिएंट चार्ली, ये क्वेश्चन कम आते हैं बेटा। क्वेश्चन जो आते हैं वो ट्रिकी आते हैं। जैसे दे मे टेल यू योर शिप वाज एट ए बर्थ, यू फाउंड आउट दैट there was a 3 degree west deviation, the vessel changed its berth and the deviation is 2 degrees east now. Explain how this change of deviation occurred. So इस पे आपको कॉन्सेप्ट अप्लाई करने पड़ेंगे। सो मैं बिल्कुल बेसिक से शुरू कर रहा हूँ बेटा। हम सबसे पहले मैग्नेटिज्म ऑफ द अर्थ से शुरू करेंगे एंड वी विल मूव ऑन टू शिप्स मैग्नेटिज्म, और फिर हम शिप्स मैग्नेटिज्म को डिटेल में करेंगे विच आर नोन एज कोफिशिएंट्स। So ready ho beta, shall I put on the presentation and we start? Okay.
Yes, sir.
Just so let's go into the presentation. Let me set it up beta. I'll put up the presentation. This is our first presentation on magnetic compass. And in this presentation, we are going to learn about the basic properties of magnets and also the Earth's magnetism, the magnetic behavior or the magnetic properties shown by the Earth. Now, our magnetic compass consists of a magnet and it gives us a directional reference basis these two. It follows the magnetic properties shown by the magnets, and the directive force is generated or caused because of the Earth's magnetism. So learning about these basic properties and the Earth's magnetism forms the basis of understanding the magnetic compass. We first go into the basic concepts of magnetism. Magnetism is a physical phenomena by which some materials like iron, nickel, and cobalt are attracted towards magnets. Now, these kind of materials which are attracted toward magnet are known as ferromagnetic materials. These ferromagnetic materials can also be converted to magnets themselves, and we have two different methods which can be used to convert them into a magnet. These methods are number 1 by use of permanent magnets and number 2 through the presence of a magnetic field. We are going to discuss these methods now one by one. Okay beta, moving on to next slide now.
Okay.
A ferromagnetic material can be converted into a permanent magnet by using two different methods. If a ferromagnetic material like iron is stroked in one particular direction, as we can see in this particular diagram, we see an iron bar which is placed here and we see a permanent magnet. The iron bar is being stroked by this permanent magnet in one particular way. If this process is repeated at least 40 to 50 times, the iron bar then starts to behave like a permanent magnet itself. The second method in which a ferromagnetic material can be converted into a permanent magnet is if a ferromagnetic material is exposed to a magnetic field and is worked upon. By working upon, we mean that the material is hammered, it is cut into pieces, the material is bent, it is welded, the material is exposed to high temperature, it is exposed to high voltage currents. All these things, if they are done on the material, it gets converted into a permanent magnet. The best example of this method would be when a ship is being built in a yard. The ship is made up of mild steel, which is a ferromagnetic material, and the ship is also exposed to the magnetic field of the earth. At whatever location the ship is, it is being exposed to the magnetic field generated by the earth. And the structures of the ship, which are extensively worked upon, like the hull plate, the keel, the decks, or the bulkheads. These materials, exposed to a magnetic field and extensively worked upon, acquire permanent magnetism and get converted into permanent magnet themselves. Now, using both these methods, if a ferromagnetic material is converted into a magnet, this type of magnetism is permanent magnetism. That means it stays with the material even after the process is completed. The material is permanently converted into a magnet. Any doubts up to here, beta?
No, sir.
Very good, beta. Great. Now, a ferromagnetic material can also be converted into a temporary magnet, and this is known as induced magnetism. This happens when the ferromagnetic material is in the presence of a magnetic field. To understand this, let us visualize that we have a box full of iron nails and paper clips. We take a strong permanent magnet and we put it in this box. Now, as soon as you take out this permanent magnet, you will see that a lot of nails and a lot of paper clip will be attracted towards that magnet, and they will be hanging on to the magnet, as you can see in this particular image. Now, these paper clips or nails were not showing any magnetic properties till the time they were in the box. But as soon as they come close to a permanent magnet, they start behaving like magnets themselves. So all these iron nails and paper clips have now become magnets, and they have started attracting other paper clips and other nails. The first nail or the first paper clip is attracted towards the permanent magnet, but all subsequent paper clips or all subsequent nails are getting attracted to other nails because all of them have converted into magnets. Now, this magnetic behavior is because of the presence of a magnetic field. This permanent magnet which we have here in this diagram shows magnetic field around its location. We have the magnetic field around a permanent magnet, and whatsoever ferromagnetic material is present there, it starts behaving like a magnet. If we remove this permanent magnet from the scene, we take it away from the nails or the paper clips, immediately all the nails are going to lose their magnetic property and they will fall down. Now, this kind of magnetism is temporary in nature. This magnetism is going to stay only till the time the magnetic field is present. As soon as the magnetic field is over, they are going to lose their magnetic property. So this is temporary in nature, and this type of magnetism is known as induced magnetism. Beta, any doubts up to here?
Yes, sir.
बोलो बेटा.
सर जो आपने अभी जो बताया जो नेल्स है वो सारे बॉक्स के अंदर में, तो वहां पे बॉक्स के अंदर में फॉर एग्जांपल जैसे आपने एग्जांपल दिया अभी के बॉक्स के अंदर में क्या मैग्नेट मैग्नेट भी उसी के अंदर में रहेगा, या वो जस्ट बिकॉज ऑफ अर्थ मैग्नेटिक फील्ड वो एक बिहेविंग लाइक अ मैग्नेटिक फेरोमैग्नेटिक?
नो बेटा, अर्थ्स मैग्नेटिक फील्ड तो बॉक्स के अंदर भी एक्ट कर रहा है, पर अर्थ्स मैग्नेटिक फील्ड की पावर बहुत कम है बेटा. सो देयर मैग्नेटिज्म, इंड्यूस्ड मैग्नेटिज्म विल बी वेरी वेरी वीक, नेग्लिजिबल. पर जब आप एक परमानेंट मैग्नेट उनके पास लाओगे जिसका मैग्नेटिक फील्ड स्ट्रॉन्ग है, दैट विल इंड्यूस द मैग्नेटिज्म इन द पेपर क्लिप्स एंड नेल्स.
ओके, जस्ट बिकॉज कि वो एक फेरोमैग्नेटिक है, तो मैग्नेटिक जैसे ही उसके मैग्नेट सामने आएगा तो वो उसको नेचुरली एक दूसरे को जितना भी है वो एक दूसरे से इंटरकनेक्टेड करके जितना उसमें पावर होगा वो पावर को डिलीवर करता जाएगा, और जितना वो कनेक्ट कर सकता है वो कर लेगा उसको.
Right, beta. Whenever any ferromagnetic material comes under the magnetic field of a magnet, it will start behaving like a magnet. जितना वो मैग्नेटिक फील्ड स्ट्रॉन्ग होगा उतना ही पावरफुल मैग्नेट बनेगा. ओके बेटा, ग्रेट. मूविंग अहेड. When we use the induced magnetism method to make a magnet, the strength of the induced magnet depends upon two factors. The first factor is that stronger the inducing field, stronger will be the induced magnet generated. So how powerful magnet are these nails and paperclip going to become depends upon how powerful this parent bar magnet is. The more powerful this parent bar magnet is, the more powerful these paper clips and nails will be. This is the first factor which decides the strength of a induced magnet. The second factor which decides the strength of a induced magnet is the alignment of the ferromagnetic material with the magnetic field lines. If the ferromagnetic material is perfectly aligned with the inducing field, there will be maximum induction generated, resulting in a strong magnet. And if the ferromagnetic material lies perpendicular to the inducing field, there will be negligible induction, resulting in a very weak magnet. You can understand it easily from this diagram. We have a magnetic field in this particular area, and these vertical lines going upwards show the direction of the magnetic field. Now we have some ferromagnetic materials and we place the ferromagnetic materials in this magnetic field. Now this ferromagnetic material, you can follow the laser pointer. This ferromagnetic material is perfectly aligned with the magnetic field lines and it shows maximum magnetic induction, making it a very strong and powerful magnet. Now there is another ferromagnetic material. You can follow the laser pointer. This material is lying at right angles to the magnetic field. Now since it is perpendicular or at right angles to the magnetic field, it shows negligible induction or no induction at all. We have a third ferromagnetic material which is partially aligned with the magnetic field. You can see it is approximately at a 45-degree angle to the magnetic field. Now since it is partially aligned, it is partially induced, and the power of this magnet, induced magnet, will be a partial power.
Sir, can you give any example?
Example of induced magnetism, beta?
यस सर, अभी जो आपने पैरेलल और परपेंडिकुलर में है ना, तो इसका कोई ऐसा एग्जांपल है जैसे पहले आपने दिया था जो मैग्नेट नेल्स उसमें सारे एक दूसरे से कनेक्टेड थे, ऐसा कोई एग्जांपल टू गेट द क्लियर विजिबिलिटी?
ओके बेटा, जब हम शिप स्ट्रक्चर का मैग्नेटिज्म देखेंगे ना तब ये चीज आपको क्लियर हो जाएगी.
ओके.
यू कैन इमेजिन जो यहाँ पे हमने फेरोमैग्नेटिक मटेरियल शो किया है, आप इमेजिन कर सकते हो कि वो एक शिप है. इफ द शिप इज ऑन नॉर्थ और साउथ हेडिंग, तो हमारे जो 4.5 लॉन्जिट्यूडनल हैं उनमें मैक्सिमम इंडक्शन होगी बिकॉज अर्थ्स मैग्नेटिक फील्ड रन्स फ्रॉम साउथ टू नॉर्थ. कैन यू विजुअलाइज दैट?
यस सर.
अगर वही शिप 090 के कोर्स पे आ जाए तो हमारे 4.5 लॉन्जिट्यूडनल पे इंडक्शन 0 हो जाएगी because they are at right angles.
Yes, yes. This is what I wanted. Thank you, sir.
Okay, beta. Moving ahead now. Once a ferromagnetic material is converted into a magnet, a permanent magnet or a induced magnet, in both the cases, it acquires two poles. It acquires a red pole and a blue pole. And it also generates a magnetic field around it. Like you can see in this particular diagram, we have a magnet. It is having two poles, the red pole and the blue pole. And these dotted lines, which are extending outside the physical body of the magnet, they represents the magnetic field exhibited or shown by this particular magnet. Now these lines, dotted lines, which represents the magnetic field of the magnet, are known as magnetic lines of force. These magnetic lines of force, they always come out from the red pole of the magnet and they re-enter into the magnet through its blue pole. As you can see in the diagram, from the red pole side, all these magnetic lines of force, the direction of the arrows show that all these magnetic lines of force are coming out of the magnet. And through the blue end, all these magnetic lines of force are re-entering back into the magnet. In other words, you can also say that these magnetic lines of force, from whichever end they come out, that has the red polarity, and to whichever end of the magnet they are re-entering back into the magnet, that has the blue polarity. Any doubts up to here, beta? Very good, beta. Moving ahead. Let us now see how do these magnets interact when they come close to other magnets. If we bring two magnets close to each other, they can show attraction between them or they can show a repulsion or a repulsive force between them. Whether they will attract or repel each other depends upon the poles which are brought together. When the unlike poles of two magnets are brought together or brought close, they attract each other. Like you can see in the first case, the blue pole of a magnet is being brought close to the red pole of another magnet, and the opposite poles or the unlike poles of the magnet attract each other. So you will see the poles tending to attract. A force appears which makes the poles attract towards each other. And if we bring the like poles or the similar poles of two magnets close to each other, they show a repulsion. They start to repel each other. A repelling force appears. So you can see in the second case, the red and red poles of two different magnets being brought close show a repulsion. Likewise, if we bring a blue pole close to the blue pole of another magnet, again being similar poles, they will repel each other. Any doubts, beta? Very good. Moving ahead. Now we go into one more very important property of a magnet. Now every magnet is going to have a magnetic field around it. In the area surrounding that magnet, there will be a presence of a magnetic field. Now the strength or power of this magnetic field is not uniform at all the locations around the magnet. The strength or power of this magnetic field keeps on changing depending upon the location. Now let us try to understand how this power of the magnetic field or strength of the magnetic field varies. Now we can see a bar magnet here in the diagram. If we draw a line joining both the poles of the magnet and extend that line, this is known as the axis of this bar magnet. And any position in the direction of the axis of the magnet is known as a end-on position. You can see it here also. End-on position means along the axis of the magnet. And if you go perpendicular to the axis of the magnet, we go in a direction perpendicular to the axis of the magnet, this is known as broadside on position. Exactly like a ship, if you extend the fore and aft line and if you have any target there in that location, it's called as end on. And if you draw a imaginary line around the beam of the ship in the outward shape direction, that's called a broadside on position. So same way, perpendicular to the axis, any position here is known as a broadside on position. So you can see it here. It is at right angles to the axis of the magnet. Beta, someone had a doubt? Ask me please. बेटा किसी भी मैग्नेट में जो रेड और ब्लू पोल्स हैं, अगर आप उनको ज्वाइन कर दो यूजिंग ए लाइन and you extend that line, that direction is known as end-on direction. Okay, and perpendicular to that is known as broadside on position. Okay, beta, चलें आगे. Okay.
So what if the magnet is square in shape then?
Okay, even if it is a square or a sphere or a cube, cuboid, anything beta, it will always have the poles at some particular direction, at some of the edges. The poles cannot be all around the magnet. They will be concentrated at some places on the edges, and we will need to find out those two locations. If you draw a line there, that is known as the end-on line. Clear, beta?
Okay, so the line joining the pole through the magnet is end-on position, correct?
Right, beta. When you extend that line, that is known as the end-on location or end-on position.
Okay, sir. Thank you.
Okay. Now, how does the strength of the magnetic field vary? The magnetic field strength in the end-on position is twice the field strength in the broadside on position. Just to give you an example, if you go 1 centimeter away from this pole of the magnet and measure the magnetic field strength here, and the same thing is done at broadside on position. You go 1 centimeter away in the broadside on position and measure the magnetic field strength here, you will see that the field strength at end on position is twice as powerful as compared to the field strength at the broadside on position. Any doubts in this, beta?
So this broadside means exactly the center of that broadside, or
no, beta. Broadside means perpendicular to the axis. Broadside means perpendicular to the axis. It is something like a beam direction on a ship.
Okay, sir, but that red dot, if it is like very close to the orange portion of the magnet, then also it will be twice. Like
no, beta.
Twice,
it has the broadside on position has to be symmetrically placed between the two poles. अगर आप किसी भी पोल और रेड डॉट के बीच में जाओगे तो फिर मैग्नेटिक फील्ड स्ट्रेंथ चेंज होती रहेगी बेटा. एंड ऑन पोजीशन पे ये मैक्सिमम है, रेड डॉट वाले लोकेशन पे ये मिनिमम है और इनके बीच में ये वेरी करेगी बिटवीन द मैक्स एंड मिनिमम.
ओके सर.
ओके
सर एक डाउट था सर.
बोलो बेटा.
सर ये 1 सेंटीमीटर जैसे सर ब्लू वाले एज से लिया 1 सेंटीमीटर, तो इधर जो 1 सेंटीमीटर परपेंडिकुलर वो एक्सिस से या फिर सर एज से लेंगे?
Beta, does not matter when we are talking of the shape. It is basically from the surface of the magnet.
Okay.
Okay, moving ahead.
And broad side on will be on either side, right?
That's right, beta. It will be on both the sides.
All right.
Let us now move into the magnetism of the Earth. Now, Earth has magnetism of its own, and the magnetic field of the Earth is identical to the field of a short bar magnet. The magnetic field of the Earth behaves exactly as if God or nature has inserted a powerful short bar magnet inside the Earth. As you can see in this particular diagram, we have the Earth here, and its magnetic behavior is exactly similar to as if there is a short and powerful bar magnet fitted by God or nature inside the Earth in this particular orientation. Now the blue pole of this short bar magnet of the Earth points very close to the geographic North Pole. You can see this green color line going up to this particular point here. This is the geographic North Earth. And the red pole of this magnet, short powerful bar magnet, points close to the Earth's south geographic pole. So you can see this green line being extended down below. This green line basically represents the axis around which the Earth rotates. And the points where this axis meets the surface of the Earth are known as the geographic pole. So you can see the geographic North Pole at the top of the diagram where the green color line intersects the surface of the Earth. And you can see the geographic South Pole at the bottom of the diagram where this green color line intersects the surface of the Earth. Now, if we extend the axis of this short bar magnet, you can see there's this yellow color line in the diagram which shows the axis of the short bar magnet of the Earth. Now these axes, they go and cut the surface of Earth at two particular points. The point which is close to the geographic North Pole, where the axis of the bar magnet cuts the surface of Earth, is known as the magnetic North Pole. And if we extend this magnetic axis, the point where it crosses the surface of Earth close to the geographic South Pole, this point is known as the magnetic South Pole. Important thing which you can see from this diagram is that the magnetic North and South poles are not at the same location where the geographic North and South poles are. The magnetic North and South poles are slightly away from the location of the geographic North and South poles. Geographic poles are defined by the rotation of the Earth, and the points of the geographic poles on the surface of Earth are fixed. They are permanent poles, they are fixed, stationary and not moving at all. They have been there from thousands of years. On the other hand, the points where the axis of the Earth's bar magnet cut the surface of Earth are known as the magnetic poles. These magnetic poles are not fixed. They are not stationary. They are dynamic in nature and they keep on changing their location slowly with time. So your doubts beta up to here?
That is why the chart is having the variation given for the year.
That's right, beta. You see a change in variation happening because of this only. Okay, great. Moving ahead now. Let me now show you the motion of the Earth's north magnetic pole over the years. In this diagram, you can see this is a zoomed in diagram of this particular portion of the Earth's surface. The apex of the cone, this particular point, represents the north geographic pole. And as we discussed, the north geographic pole is fixed or stationary point on the surface of Earth, and it has been there from thousands of years and it does not change its position. The magnetic north pole of the Earth, on the other hand, is dynamic and keeps on changing its location slowly. You can see the movement or the motion of the north geographic pole represented by this dotted line in the diagram. This is how the magnetic north pole of the Earth has been changing its location over the years. 1600, 1700, you can follow the laser pointer. Then at 1800, then this was the location of the magnetic pole at 1900, 1948, 1994, 2000, 2007, and still moving further. Moving ahead, beta. Now, a few more important points related to the Earth's magnetism. We have seen that the magnetic poles of the Earth are not stationary and they keep on changing their location. The geographic poles are stationary. Now, the difference between the direction of a geographic pole and a magnetic pole at any particular place from the Earth, if you find the angle between the geographic pole and the magnetic pole, that is the variation at that particular place. The geographic poles are the references for giving us true directions, and the magnetic poles are the references for giving us the magnetic directions. A unaffected magnetic compass will point its poles or point its direction towards the magnetic pole, and to get the geographic pole or to get the true directions, we have to apply variation to the magnetic direction. And once we apply the variation to the direction given by the magnetic compass, we obtain the true direction. Now, second important thing to understand is that nature or God has made the Earth such a magnet that its blue pole is close to the geographic north pole, and the red pole of the Earth's paramagnet is close to the geographic south pole. Now, we are aware that for any magnet, red pole is the one from where the magnetic lines of force come out of the surface of the magnet and they re-enter into the magnet through the blue pole. So you can see it clearly here. From the south magnetic pole of the Earth, which has a red polarity, you will see that all the magnetic lines of force are coming out of the south pole. You can have a look at the arrows representing the direction of the magnetic field lines, and you will see that these magnetic field lines are coming out of the red pole or of the south magnetic pole of the Earth. So anywhere in the southern hemisphere, you will see that these magnetic lines of force are coming out of the surface of Earth. These magnetic lines of force, they go back into the Earth at its blue pole or the north magnetic pole of the Earth, and you can see that anywhere in the northern hemisphere, the magnetic lines of force are going into the surface of the Earth. So any doubts up to here, beta? Very good, beta. Moving ahead. Another important thing to note here is that since the Earth's north magnetic pole has a blue polarity, the Earth's north magnetic pole will be attracting the red pole of any magnet on the surface of Earth. So if we have a freely suspended magnet on the surface of Earth its red pole will be attracted by the north magnetic pole of the Earth, which has a blue polarity. We are aware that opposite poles of a magnet attract each other. So the blue pole of the Earth attracts the red pole of a freely suspended magnet, and the red pole of that freely suspended magnet gives us the magnetic north direction. Is that clear, beta?
Sir, this means that any suspended magnet that on Earth will attract towards the North Pole.
The red end of that magnet will point towards the blue end or the north magnetic pole of the Earth.
Yes, sir.
Okay, moving ahead. We can now see another diagram showing us the magnetic field lines of the Earth. Now, a very important aspect of these magnetic field lines is the angle at which they cut the Earth surface. We are aware that the south magnetic pole of the Earth has a red polarity, and all magnetic field lines, they come out of it. And as you can see here also, in the southern hemisphere, anywhere you see, the magnetic lines of force are coming out of the Earth's surface. We know the north magnetic pole of the Earth has a blue polarity, and all magnetic field lines, they enter into that blue pole. And you can see everywhere in the northern hemisphere, the magnetic field lines are going into the surface of the Earth. A very important property which should be clear in our mind related to these magnetic lines of force is their angle of cut. Now, if you look carefully, these red color arrows represents the magnetic poles of the Earth. Now, at the south magnetic pole of the Earth, you see these magnetic lines of force, they are coming vertically out from the Earth's surface. In other words, you can see they are making a right angle to the Earth's surface. They are perpendicular to the Earth's surface, or you can say the magnetic field lines are vertical at the location of the south pole. Now, from the south pole, as you go towards the equator, you will see that the angle of these magnetic field lines with the Earth's surface starts to reduce. At the pole, this angle of cut between the magnetic field line and the Earth's surface was 90 degrees. As you move away from the pole towards the equator, the angle starts to reduce, maybe 80 degrees here, 70, 60, 50, 40. And as you go further and you come close to the equator, now at the equator, you will see that the magnetic field line's angle of cut becomes 0. The angle of cut was 90 at the pole. Coming close to the equator, the angle starts to reduce, and at the equator, the angle becomes 0. Angle becoming 0 means that these magnetic field lines are parallel to the Earth's surface. Now, as you move towards the north magnetic pole, again the angle starts to increase. Now the lines are going into the Earth's surface, but the angle starts to increase, maybe 10 degrees here, 20, 30, 40, 50, 60. And when you reach at the north magnetic pole, the angle of cut between the magnetic field lines and the surface again becomes 90 degrees. You can see at the north magnetic pole, the lines are again perpendicular, making a 90-degree angle to the surface of Earth. Now this angle is known as the magnetic dip or a magnetic dip angle. It is also sometimes called as the magnetic latitude of a particular place. You can see at the magnetic equator, this angle was 0. So the magnetic latitude of that place was 0. As you move towards the pole, the angle is increasing. Magnetic latitude is also increasing. And as you reach at the pole, the angle of cut becomes 90 degrees. The magnetic latitude at the pole also becomes 90 degrees. Another important thing which you will see from the diagram is you have the geographic poles also represented by the dotted lines, and we have the magnetic field lines also. We have the geographic equator also. Geographic equator is a great circle exactly midway between the geographic poles. You can follow the laser pointer. it shows the geographic equator now. This geographic equator is a perfect great circle. It follows geometry and it is a perfect great circle. Whereas the magnetic equator is not a perfect great circle. Magnetic equator is represented by this curved line. It is not a perfect great circle. The reason being magnetism is a dynamic property of the earth. So it is not a perfect great circle, but a curved line. Now using the angle of dip or the angle of cut between magnetic lines and the surface, we can define the magnetic poles as well as the magnetic equator. Let us see what is the definition of magnetic poles. Magnetic poles are defined as those points where the Earth's magnetic field lines are vertical or they are perpendicular to the Earth's surface. As you can see in the diagram, at the location of the poles, the magnetic lines of force represented by red arrows are perpendicular to the Earth's surface. They are making a 90 degrees angle. Any doubts up to here, beta? Very good, beta.
No.
Excellent. Let's move ahead. And using the same dip angle, now we can also define the magnetic equator. The magnetic equator is an imaginary line on the Earth's surface, joining those points where the Earth's magnetic field lines are horizontal or parallel to the Earth's surface. So you can see at this particular point here, the magnetic field line is parallel to the Earth's surface. The Earth's surface is in the up and down direction here. The magnetic field line is also in the up and down direction here. The field line is parallel to the Earth's surface. And if we join all these points on the Earth's surface where the magnetic field lines are parallel, this creates or this marks the magnetic equator. Now, as discussed earlier, the angle at which the lines cut the surface of Earth is known as the dip angle. And this diagram shows the dip angle very clearly. You can see the angle of cut between the magnetic field lines and the Earth's surface at all the locations. Let us now see the definition of the dip angle. This angle which the Earth's magnetic field makes with the Earth's surface or the horizontal is known as the dip angle. As we can clearly see in this diagram, the dip angle is 0 at the equator and is maximum 90 degrees at the poles. Any doubts up to here, beta? Very good, beta. Excellent. Let's move ahead. Now this dip angle can be measured using an instrument which is known as the dip meter. The dip at any place can be observed using an instrument named as the dip meter or a dip needle, which you can see in the diagram. Now in this dip needle or a dip meter, you see we have a magnetic needle, and this magnetic needle is free to swing in a vertical plane. There is an axis or swivel at the center here, and this magnetic needle is free to swing or move in the vertical plane. There is a scale which is provided. The scale gives us the dip angle. Like right now you can see that the dip angle is being given as, you can see 10, 20, 30, 40, 50, 60. The dip angle which is shown here is close to 64, 65 degrees. The needle is free to swing in the vertical plane, and when we use this instrument is first aligned in the north-south direction using a compass, and once it is aligned to the north-south direction, this needle is usually locked initially in the horizontal plane, and as soon as you remove the locking, the needle swings up and down and settles down, showing us the dip angle. Any doubts?
Sir, do you have any video of this? Any video of this?
हाँ बेटा, okay, I'll show you. Let us complete the presentation, then I'll show you.
Okay.
If this dip meter is placed anywhere in the northern hemisphere, we know the north magnetic pole of the earth has a blue polarity. So that blue pole of the earth is going to attract the red pole of our needle. So the red end or the red pole of our needle will point downwards in the northern hemisphere. And if this instrument is placed in the southern hemisphere, the southern magnetic pole of the earth has a red polarity. It will be attracting the blue pole of the dip needle. So in southern hemisphere, the blue pole will dip downwards and the red pole will be pointing upwards. Conventionally, dip is designated as positive in the northern hemisphere. We now have another diagram showing very clearly the magnetic field of the earth as well as the dip being recorded by a dip needle. You can see this is the earth surface. We can see the magnetic lines of force. The arrows show the direction in which they are going. In the southern hemisphere, they are coming out of the earth's surface, and in the northern hemisphere, they are going down into the earth's surface. This is the short bar magnet assumed to be fitted inside the earth, and you can see this is a magnetic equator. If we have a dip needle placed at the magnetic equator, the dip needle pointing in the direction of the magnetic lines of force will be parallel to the earth's surface. It will be horizontal, showing us the dip as 0. Now as we proceed towards the North Pole, at this particular location, the dip needle again aligns itself with the magnetic lines of force, and you see the red end of the dip needle will now be attracted by the blue end of the Earth's north magnetic pole, and it will show a downward dip. As we keep moving closer to the North Pole, this dip angle starts to increase. It keeps on increasing, and as we reach exactly at the North Magnetic Pole, you see the magnetic lines of force are vertical here, and the dip needle will be pointing exactly downwards. The red end of the dip needle will be pointing exactly downwards towards the blue end of the Earth's North Magnetic Pole. You can also see the geographic North Pole. It is at a different location from the magnetic North Pole. So you can see the dip angle starting from 0 at the magnetic equator, increasing and going up to 90 degrees at the magnetic pole. Any doubts up to here, beta?
Sir, I'm seeing that you will be in the South Pole.
Ask again, beta. Your voice was dull. Can you speak little slowly?
Sir, I'm seeing that you will be in from equator to South Pole.
I still did not get you, beta. From equator to South Pole, the red end will be pointing away from the Earth's surface, and the angle would increase from 0 to 90 as you go from equator to South Pole. At the South Pole, red will be pointing upwards and blue will be pointing downwards.
Okay, sir.
Okay. Okay, beta. Great.
सर
So,
पहले जो आपने दिखाया था सर जो डायग्राम, उसपे जो निडल रेड कलर का निडल जो नीचे की तरफ था 65 डिग्री पे, दैट मींस दैट टाइम that one was in southern hemisphere, correct?
No बेटा, this is in the northern hemisphere, क्योंकि रेड तो नॉर्थ में ही नीचे पॉइंट करेगा ना बेटा, नॉर्थ में ब्लू पोल है।
सॉरी हाँ, नॉर्थ, यस सॉरी नॉर्दर्न हेमिस्फीयर में वो करेगा क्योंकि रेड उसका जो है एंगल दिखा रहा था वहां पे 65.
Yeah, that's
okay,
great.
yes, sir.
That's right. Okay, all right. Let's move ahead.
Sir, one question. This dip angle is that also the magnetic latitude?
That's right, beta. It is same as magnetic latitude.
Okay, sir.
Okay. Now we have understood that the magnetic field lines cut the surface of Earth at any particular angle from 0 degrees to 90 degrees depending upon the location. We have selected a particular location on the Earth's surface where the magnetic field lines are in this particular orientation. They are going down into the surface of the Earth, so that tells us that this is the northern hemisphere, and they are making this particular angle. This is the dip angle. So the angle of the magnetic field lines with the horizontal or with the surface of Earth is the dip angle. You can see the dip angle here. Now the magnetic field in this particular direction is represented as total field intensity of the Earth's magnetic field. Now this total field intensity or the magnetic field of the Earth is broken down into two components for our use, for our utility to understand the magnetism better. These two components are, one is the horizontal component, which is known as H or HF, a short form for horizontal force. This horizontal component of the total magnetic field of the Earth, which is known as H or HF, is what makes the compass point towards the magnetic poles. This H or HF basically provides the directive force to our compass. The H or HF horizontal force is maximum at the equator, as the magnetic field lines at the equator are perfectly horizontal, and the H component reduces with the increase in latitude of the observer, becoming nil at the magnetic poles, because the magnetic field lines at the poles are perfectly vertical, making the horizontal component 0. Therefore, the directive property of a magnetic compass, which is based on or dependent upon H or HF, the horizontal component, is highest at the equator and starts to reduce when the vessel proceeds towards the pole, eventually becoming nil at poles. This is exactly the reason that as we move into higher latitude, the magnetic compass starts to lose its directive force. After we cross a latitude of 70 degrees north or south, going towards the pole, the compass becomes highly unreliable. Go ahead with your doubt, beta.
Sir, can you
I
explain?
didn't understand this horizontal component, sir. ये क्या है एक्चुअली?
ओके बेटा, आपने बेटा अभी
टोटल फील्ड इंटेंसिटी तो समझ में आ गया सर कि वो नीचे से निकल के वो जा रहा है इक्वेटर के बाद में वो अर्थ की तरफ घुस रहा है, टोटल फील्ड इंटेंसिटी, बट ये हॉरिजॉन्टल कंपोनेंट ये क्या है सर?
ओके बेटा, डू यू रिमेम्बर द वेक्टर रेजोल्यूशन बेटा, जो हमने +1 +2 में किया था? वेक्टर रिजॉल्व करते थे ना दो कंपोनेंट में, हॉरिजॉन्टल और वर्टिकल, एक्स एक्सिस वाई एक्सिस।
यस सर।
एग्जैक्टली वही चीज हमने की है बेटा। जो हमारा टोटल फील्ड है अर्थ का मैग्नेटिक फील्ड, हमने उसका हॉरिजॉन्टल कंपोनेंट और वर्टिकल कंपोनेंट अलग अलग कर दिया है टू अंडरस्टैंड इट बेटर।
सर, आपका कहने का मतलब है जो मैग्नेटिक फील्ड अर्थ मैग्नेटिज्म है, किसी पर्टिकुलर पॉइंट पे वहां पे जो कंपोनेंट जो टोटल फील्ड इंटेंसिटी है उसका वेक्टर डिवाइडेशन कर दिया, तो जो हॉरिजॉन्टल कंपोनेंट है उसका जो एंगल बन रहा है वो डिप है।
बेटा डिप तो हमेशा हॉरिजॉन्टल के साथ ही बनता है। हमने यहाँ पे टोटल फील्ड इंटेंसिटी को दो कंपोनेंट में डिवाइड कर दिया है ताकि हम इसे इजीली अंडरस्टैंड कर सकें।
सर फिर ये डिप जो होगा वो इक्वेटर पे 0 होगा, करेक्ट?
सर्टेनली बेटा, इट इज 0 एट द इक्वेटर।
ओके, एंड सेकंड थिंग, आपने कहा कि मैग्नेटिक कंपास जो है दैट इज लाइक वी कैन नॉट यूज मोर देन 70 डिग्रीज नॉर्थ और साउथ।
We can use, but it becomes
जाइरोस्कोप में भी होती है।
unreliable. We can use, but it becomes unreliable, बेटा, unsteady.
ओके, बट ये सेम चीज तो जाइरोस्कोप में भी होती है, लाइक इफ वी मूव फर्दर नॉट टू 70
Yes,
डिग्रीज देन वी
that's
कैन
right.
नॉट यूज जाइरोस्कोप।
Yeah, that's right. You cannot use it. वो मैं आपको तब समझाऊंगा जब जायरो करेंगे।
ओके, ठीक है।
ओके
सर ये थोड़ा डायरेक्टिव के बारे में एक्सप्लेन कर दीजिए, उसका कुछ
ओके बेटा, बड़े इजी भाषा में इसको समझो। हमने अर्थ के टोटल फील्ड को हॉरिजॉन्टल और वर्टिकल कंपोनेंट में डिवाइड कर दिया, सही बात है, डिवाइड कर दिया।
यस सर।
हमारी जो कंपस है जो शिप पे लगी है बेटा, वो कौन से प्लेन में काम कर रही है? इज इट इन द हॉरिजॉन्टल प्लेन और इज इट इन द वर्टिकल प्लेन? हमारा जो कंपस
Horizontal.
कार्ड है हॉरिजॉन्टल प्लेन में है, तो नेचुरली जो अर्थ का हॉरिजॉन्टल कंपोनेंट होगा वही हमारी कंपस को डायरेक्शन देगा बेटा।
यस सर।
समझ गए?
यस सर। सर ये
और
डायरेक्टिव फोर्स का नहीं लग रहा।
अब बेटा डायरेक्टिव फोर्स का मतलब है ऐसी फोर्स जो कंपस को डायरेक्शन देती है, उसी का नाम है डायरेक्टिव फोर्स। समझ गए बेटा?
यस सर।
ओके
सर तो डायरेक्टिव फोर्स इन दोनों का रिजल्टेंट बेसिकली हॉरिजॉन्टल और वर्टिकल का, जो जिसके ज्यादा है उस तरफ जिस तरफ टिप मतलब वो नीडल घूम रहा है, दैट इज अ
ना बेटा,
डायरेक्टिव
ना ना
फोर्स।
ना ना, तुमने तो बेटा खिचड़ी बना दी। डायरेक्टिव फोर्स इज ओनली द हॉरिजॉन्टल कंपोनेंट बेटा। द वर्टिकल कंपोनेंट डज नॉट अफेक्ट अवर कंपस नीडल एट ऑल। वर्टिकल कंपोनेंट कंपस नीडल को बिल्कुल अफेक्ट नहीं करता है। हॉरिजॉन्टल कंपोनेंट गिव्स द डायरेक्टिव फोर्स। क्लियर है बेटा?
नहीं सर, एक बार मतलब नहीं समझ आया ये वाला टॉपिक, ये वाला
ओके
टर्म।
बेटा ओके। आपका जो कंपस नीडल है, जो कंपस कार्ड है बेटा, वो कौन से प्लेन में घूमता है? हॉरिजॉन्टल में घूमता है या वर्टिकल में घूमता है? हॉरिजॉन्टल में घूमता है।
हाँ,
अगर आप,
हॉरिजॉन्टल में, हाँ सर।
बिल्कुल सही, अगर आप अपने कंपस कार्ड के बिल्कुल ऊपर या नीचे कोई भी मैग्नेट लेके आओगे, ये आपके कार्ड को बिल्कुल अफेक्ट नहीं करेगा, बिकॉज वर्टिकल डायरेक्शन का मैग्नेटिज्म हॉरिजॉन्टल कार्ड को अफेक्ट नहीं कर सकता है। किसी भी वेक्टर का इफेक्ट 90 डिग्री जाने पे जीरो हो जाता है बेटा।
हाँ सर, वो सेंटर में 0 होता है, वो पता है, वो तो ठीक है।
That's the reason that the vertical component does not affect the compass card. It does not give us any directive force. Clear बेटा? चलें आगे।
Sir, when same magnet is brought in horizontal of compass card, so it that compass card pointed towards that magnet, right? Sir?
Certainly बेटा, that's right. That's right.
So that-
That's right. The other component of the total field intensity of the Earth, which is the vertical component, is known as Z component. Now, as we have discussed under the dip angle, this Z component will be acting downwards in the northern hemisphere, and this Z component will be acting upwards in the southern hemisphere. In the northern hemisphere, the magnetic field lines go down, so the Z component acts downwards. In the southern hemisphere, magnetic field lines come up from the earth's surface, so the vertical Z component acts upwards. This Z component or vertical component does not affect the directive property of our compass in any way. It does not enhance or does not diminish the directive property of the compass. This Z component, however, affects the magnetism of the ship, which we will discuss under the head of ship's magnetism. Clear बेटा? चलें आगे। Very good. So basically हमने पहला अपना जो प्रेजेंटेशन है वो कवर कर लिया है।